All right, good afternoon, everyone, and welcome to this webinar on computational thinking with Python in maths. This webinar is part of a mini-series of webinars co-organized by the STEM Alliance, Scientix, Texas Instruments, and T-Cube Europe. Today, we will talk about computational thinking, whereas next week, we will talk about physical computing with Python in the classroom. My name is Bjorn Bachmann, and I'm project manager of the STEM Alliance, which is an initiative that brings together education and industry. And together with us in the room today, we have my colleague Alejandra Hernandez, who will be supporting this webinar from a technical point of view. So if you have any issues with your audio or connection, please do not hesitate to send her a message in the Q&A window. But most importantly, it is with great pleasure that I am welcoming our speakers for today, Koen Stulens from Texas Instruments and Bert Wikkerink from T-Cube Netherlands. Thank you so much to the two of you for being here with us today. Now, let me continue with some technical aspects. To get a greater experience out of this webinar, you can use live captions and subtitles. To activate these, you just need to go to your video controls and select captions or subtitles, and I put a screenshot here. You will also see that there is a Q&A or a question and answers window in your screen. If you don't see it, make sure you open it, because we will be sharing useful information and links with you there throughout the entire webinar. Also, as this is an interactive webinar where the audience can interact with the speakers, please feel free to share your questions in the Q&A window, and we will be collecting them and address them to the speakers in the end. And here is already the first link we're sharing with you. In the Q&A window, you can now click on the participation list to validate that you attended this webinar and receive a certificate of participation. This is to ensure that we can prove this event took place, and so that we can continue to organize these events, the events like this one, in the future. Also, if you are interested in a certificate of participation, this is the only way to request one. Now, let's move to our agenda for today. We will begin with an introduction to computational thinking by Koen. We will then move on to some mathematical examples, and later on, Bert, who will also share his insights on graphical patterns and creativity. You will be able to ask questions, as I mentioned, to the speakers throughout this webinar, and we will address them in the Q&A session towards the end. So please share your questions in the Q&A window. Well, let me now introduce you to the speakers. Our first speaker is Koen Stulens from Texas Instruments. Koen is responsible for teachers training and educational content at Texas Instruments for the Netherlands and Flanders. He has been connected to the math department of the Hasselt University, and he is author of activities and books about the value of technology in learning and teaching mathematics. Welcome, Koen. How are you today?
Doing very well. Thanks for the introduction, Bjorn.
Well, and it's great to have you here. But let me first introduce the audience to our second speaker, Bert Wikkerink, who is member of T-Cube Netherlands. Now, T-Cube, that is T with a little 3 on top, stands for Teachers Teaching with Technology. And T-Cube is an international network of teachers supported by Texas Instruments Education Technology. Now, Bert was a math teacher in secondary education for many years, and he is an experienced user of Texas Instruments technology in the classroom. He currently develops Python coding content and activities for math education. Welcome, Bert. How are you today?
Thank you for the introduction. I'm well, and I'm looking forward for the second part of this presentation.
Well, and so are we. And without further ado, I will leave the floor to you guys. Once again, for the audience, if at any point you have questions, just write them down in the chat window so we can address them later. So please, Koen and Bert, the floor is all yours.
Thanks a lot, Bjorn, for the introduction. Let me start by introducing you to a term, computational thinking. First technical issue, how can I move the slides forwards? Yeah, there you go. So this is the agenda, 2 clicks, so I need to be a little bit more patient. So if you Google the term computational thinking, you find a lot of information, a lot of definitions, but let me summarize a little bit some definitions about computational thinking, what I found throughout some reading I did in the past. So in 2006, Janet Wing described computational thinking as a thought process in formulating problems and solutions so that you be able to solve it with information processing technology. It was already in 2006. Let's move a little bit up further on. No clue what is happening here, sorry for that. The slides are not moving forward, Bjorn.
Yes, it seems to take a moment, but try it again now.
Yeah, there it is. So another company, Digital Promise, published this kind of nice picture of what is computational thinking, and they were also talking about a thought process, but it's a nice visualization of foundations and practices around computational thinking. And yeah, when you read those terms around pattern recognition, abstraction, creating algorithms, understanding systems, working with data, I think there is no doubt about the fact that all those terms are very well related or correlated to mathematics and the daily activities in a math classroom. And then another definition is not coming to the screen again, sorry guys.
No worries. You might have to click on the slides just once so you have control of the slides, and then click again to move. Exactly.
Yeah. All right. So I need to use 2 hands, technology and computational thinking. So my computational thinking is I need to use 2 hands. So this is the description of the process of computational thinking by Conrad Wolfram in his last book around MathFix, a blueprint for the artificial intelligence, a blueprint for that kind of century. So he is describing it as define, abstract, compute, interpret, and possibly when you went through that process, do it again. So let me shortly introduce this kind of process based on the pandemic COVID-19 without going into any detail. So suddenly there was a virus traveling around in our areas, and you need to define what the virus is, how does the transmission goes, and how does the incubation works for that virus. And then in the second step, you are collecting data, you are setting up contact tracing, and you're going to create a kind of abstract biostatistical model. And then in the next step, oops, I don't go back now. You have the transmission prediction based on those models you are creating. And in your last step, you start to interpret the processing of that data based on your models. And then the results you're going to reflect on the reality, and possibly it gives you a good indication of what's happening. But if not, you're going to redefine or redesign your processes, your models, etc., etc. So based on the hospitality, the people who died from COVID and the people who get infected by it, possibly you need to adapt your models. That's a brief introduction to a concept called computational thinking, how such a process works, but we are not going to make it that complicated for bringing that into the math classroom. So a last definition is a definition of computational thinking by the Dutch curriculum board, and it's a process-based formulating of problems to be solved by a computer technology or with technology in general, whatever you use. If it's a handheld, if it's a computer, whatever. So, but it's that process to solve problems with computer technology, but not only this, and the slide is not moving forward. Not at all. There it is. So it's to solve the problems with technology, but to do that, you need to have a good understanding of algorithms and procedures to bring everything together to solve the problem and to get a good result and to get good outcomes based on your processes and algorithms you are constructing. So, what does mathematics and computational thinking have in common? So if you look at the intersection of mathematics and computational thinking, you come to a kind of skills like problem solving, algorithms, analyzing, modeling, logical reasoning. And again, here it is close to what we do in the math classroom, but also when you read a lot about the 21st century skills, it's a bit like that's the intersection between mathematics and computational thinking. And how to bring that in the classroom. So I think it's not so complicated that sometimes people think to bring this in the classroom, because you have already a lot of graphing technology available in the math classroom around the world. And nowadays, all those graphing calculators or handhelds or graphing technology have in a way integrated Python. And Python is a language, one of the top 3 languages in the world, also in industry, but it's really accessible for students and even for young children. And it's also a language which is very easy to read, very easy to connect to mathematics. And a benefit here is you have a worldwide community and you have a bunch of code available in libraries. And what we are going to use in this webinar is the Inspire technology. Why am I using this? Of course, I'm working for Texas Instruments at the moment. It's the AI technology, but at the other hand, you have one interface where you can do everything. And the benefit here is that Python can communicate with all the other math applications. But everything what you're going to see from now on, you can also do with other kinds of technology, with handhelds, other handhelds, or also other software. Bang. There you go. So you saw that process of Conrad Wolfram. Let's take some freedom to convert it a little bit in structure, translate, process, and control. And take this as a first example. You rent a car, and the price for that car is 66 euros for the first 70 kilometers. And then for each extra kilometer driven, you pay another 0.3 euro. So structuring this program or this problem, yeah, here you go. So we translate it in a kind of flow chart. So the input you have here is the amount of kilometers. If the amount of kilometers is smaller than 70, the price is this 66. If not, the price is this formula, the amount of kilometers minus 70 times 0.3. And the next step, what you have to do is to translate this kind of flowchart into the Python code. And if you are familiar with Python coding, you can immediately read what is on the screen right now. But if not, you can read it as well, because it's so easy to read. It's pretty similar as the flowchart. And in the next step, you are going to process this Python code, and it gives you an output. If you drive, let's say 273 kilometers, this is the price you have to pay. And in the next step, how to go back now? Technology is not behaving very well for me today. So if you have the output, you need to control it. If it's giving you the right results, yes or no. And if yes, done. If not, you need to adjust your Python code to get the right result. So this is, in a way, the process we are using to bring computational thinking in the classroom. Please behave. Yes. So quickly, a couple of examples to show you that it's not so complicated to bring computational thinking into the classroom. So a very common used example for, let's say, middle school, upper secondary, somewhere in between, wherever you want to do it, is the Euclid algorithm to determine the greatest common divisor of two integers. And it's using the property that when you have two numbers, if you do the subtraction of the biggest one minus the smallest one, and you take that subtraction together with the smallest one, it's the same greatest common divisor. And that's what is written in this flowchart here. Subtract the smallest one as often as possible to the largest one. If it's 0, yes, you have it. If not, redo it. So this is pretty vague for a machine to do the execution and to get to the result. So we need to refine this kind of flowchart so it can be translated to a machine. So a little bit more details around this flowchart. You start with two numbers. If they are not equal, one or the other is bigger. So if A is bigger than B, then A is A minus B, and you do it again. You keep B, and in the other side, in the other way, you do B is equal to B minus A. And if it's come to A and B is the same, boom, you have the greatest common divisor, and you just print it. This was already written in the Elements of Euclid many, many years ago. And this is something that can be translated easily into an algorithm that can be executed by a machine. You put them in, you do that same. If A is bigger than B, then this. If not, then do that. That's all you have to do. And if you translate it to Python, no problem. Input two numbers. As long as they are not equal, execute this kind of if statement, and then you just print the result. And here you have it. The output of the greatest common divisor of 48 and 36 is 12. And I must say, this is possible with a lot of kids. You don't need to have a kind of programming geek to be able to transform an algorithm into a code and let a machine execute it. And that's nice for bringing all kids in contact with computational thinking, way also get a better understanding of our surrounding digital world, because everything is based on code nowadays. Let me go to the next slide. Let's try to do it again. Here you go. But this example is also a good example to introduce a program technique called recursion. So if you don't want to do this with the level of your student, you don't do it, because here you are defining a function that's calling itself when you start executing it. And here it's a bit different than in the previous algorithm. You start with determining the greatest common divisor of 1140 and 900. You make the quotient and you replace the biggest one by the remainder. And you do that a few times until the remainder is 0, and that gives you the output. So here you see the flowchart, and here you see the Python code. And what I do here is nothing else than repeating that function all over again until the remainder is 0. So, and then I create a little bit more nicer look and feel for the output, and then you say the input is A and B, and the greater common divisor of 1140 and 900 is 60. So very basic things. Let's say a couple of 15 lines, and students can reformulate, translate their algorithm into Python code and let the machine do the work. So a next example, let's go from Euclid to Pythagoras. And in a geometry app, I'm here creating a triangle, and I'm measuring the length of a triangle. And I store these values over here of the length of the sides as A, B, and C. So computational thinking and also coding also give an extra dimension on the mathematical concept variable. It also makes the concept of variable concrete, and students can work with it. So what am I going to do now? Bang. I'm going to write some code, and I'm hopefully be able to show it to you. Here you go. That check if this triangle is a right-angled triangle. So what I'm doing here is exchange variables between a geometry application and a Python code. So I create a list and I store the values A, B, C on a list. So the test I'm going to perform here is that the square of the longest side divided by the sum of the square of the other sides is equal to 1. That's a theorem of Pythagoras. So, of course, why am I using now the word longest side? Because that's not the official term in geometry, but that's the only thing that a machine can determine. What is the longest side? So the only thing is, what I'm doing is putting everything in a list and then sort the list from small to large. And that's what I'm doing here. I run the code, and the code is telling me this is no right triangle. If I now change the value or the triangle, I get other lengths. I run the code again. Yeah, it's still not a right angled triangle. And if I change the triangle again, then the system will tell me, hey, it's a right angled triangle. So you see, you have a combination here of a geometry construction, variables, what is variable, what is changing. Let the machine decide what is now the property of that triangle. And what you see here, again, on the left side, not a lot of code, very readable. Kids get not in trouble with the syntax. It's very understandable. It's communicating with the math, and it's connecting coding, computational thinking with mathematics. And I think that's very powerful about this technology, but also you can, as I said, you can do that with others as well. But the combination of linking coding with mathematics is powerful, because you create another representation of a mathematical concept, and that gives better understanding of abstract mathematical concepts. A last example before I hand it over to Bert is the Galton board. That was an instrument in 1889 invented by Sir Francis Galton to investigate the central limit theorem of statistics and how many binomial distributions are needed to approximate a normal distribution. And the idea is you have a board with some rows of pegs or pins, and the balls are rolling throughout the pins or the pegs. And the question is, what is the probability to end in one of those bins? Here at the bottom you see 3 rows, and to end up in the bin with number 0, it's 1/8. 1 and 2 is 3/8, and number 3 is also again 1/8. So that's a binomial distribution. So how can I simulate this? Because this can be pretty abstract. So what does that mean? So if I simulate a Galton board of 5 rows, what I'm doing, trying to get back, no, yes, no, here you go. So what I'm doing, I start with 0. If I hit a peg, to the left means 0, to the right means 1. So I do that 5 times, and then I end up from at one of the bins, and I just do at random 0 or 1. And with that number 0 where I start from, I just start adding 0 or 1. And then the P after 5 times is the number of the bin I landed into. And I can make it more complicated. If I want to have more than one ball, I just put a loop on it, and I do it as much as the number I create as an input, the number of balls I would like to drop throughout the Galton board. But if I do that multiple times, I also need to store it somewhere. So I create another list where I store how many balls are in each bin. So now I want to do something with that data. It's very nice that you have data, but you need to do something with it. So therefore, I create another list bin, where I create a list which represents the number of the bin, and also binom, the binomial probability to end in one of the bins. So it's, in this case, it's approximation. So I bring everything together as couples: the number of the bin, the number of balls in the bin, the number of the bin, and the approximation of the probability. And when I then run my code, there it is. I do it 500 times, so it took a while before the results were there. Then you get here in bin 0, 21 balls, etc., etc. And here you get approximation of the probabilities of this probability simulation experiments. But again, everything needs to be visible nowadays. And so, as you saw for the triangle, where I grabbed data out of the mathematical application, here I'm doing the reverse. I'm storing the data I get out of Python in a spreadsheet. And here you have my data, how many balls are in bin 0 to bin 5. And when I have all this kind of stuff in an Excel sheet, it's easily to create histograms of the number of balls in a specific bin, or the probability, or let's say the approximation of the probability of landing in a certain bin. So this is the combination of mathematical applications and Python coding to visualize and to analyze your results. If you don't like to combine it with mathematics, of course, if you use the graphical modules in Python, based on the data you see in the getting out of this code, you can also combine it with graphical programming to do everything in the Python shell. And then you see, after 500 simulation, you get this histogram, and you print or you write the results in your graphical screen. And even when you do more advanced programming, and it's a bigger project, then you end up with this nice simulation Bert made out of the Galton board, and you see the ball rolling, and you see the visualization coming up, and you see also the real data aside this experiment. Of course, this is not anymore created in 20 to 30 lines of code. Here you can make a kind of coding project out of it for your students. And with this nice example of visualization of Bert, I would like to hand it over to Bert Wikkerink. It's my colleague who is a kind of mathematician with Python code and mathematics. Up to you, Bert. I don't know if I need to do something to hand over the presenting rights to Bert, but I don't know what to do.
No, I think, first of all, thank you so much, Koen, for your introduction on the concepts and some very concrete applications. And at this point, I see that Bert has shared his screen. So, Bert, up to you.
Yes, can you hear me?
Yes, we can.
Okay. Well, Koen showed some Python coding examples, and they were all created in the software I have now on my screen. And this software is the software I use for doing some Python coding. And I want to show some examples that are not strictly mathematics, but more related to art and graphics. And but you can only make these examples by thinking algorithmic. I mean, I use simple algorithms to show some nice results. So the software works as follows. When you open your software, you see press menu. I press menu, can add a Python application.
Cannot see the screen, Bert. Sorry.
No?
No.
So I can see it. Alejandra, can you confirm that it's visible?
Yes, I can see it, and I see it on the live event, yeah. I
cannot see it, but that doesn't matter.
Okay, then I go on. I hope that everyone else can see it. When I open the menu, I can add a Python editor, give it a name, for instance, test, and then I can type in my code. Now I have done some examples in this same way. By the way, this software is also on the calculators, and you see on the calculator exactly the same that you see on the screen of the software. But I will use the menu of the software because that works better for me. I have a simple example. When computers came available for the normal people like me in the 80s and 70s of the last century, then you could use computers, but the graphical capabilities were very, very poor. When you wanted to make some art with your computer, you could, for instance, do a very simple algorithm, print letters on the screen, and for instance, I make a piece of art by using only the letter N and the letter Z, choosing it randomly and print it on the screen. When I execute the program, I see what you could call a piece of art. And this is a random piece of art because every time when a character is printed, it is randomly chosen between the N and the Z. I can run it again and I see another piece of art, but it looks the same because there are so many N's and Z's, but the reorganization is somewhat different. Now I can make another piece of art by choosing two other characters. I have the same algorithm, the same program, and when I run this, I see a kind of same piece of art, but it is somewhat different. The code I use is only two for loops, one for the horizontal and one for the vertical rows, and I use a random function that chooses a 0 or a 1, and when it's not a 0, it prints a smaller than character, and in the other case it prints a greater than character. And when I do this, I have a screen full of characters randomly chosen between the two different characters, smaller than and greater than. This is what you could call what you could call computer generated art, but then in a very basic way. Now you can make it somewhat complicated by doing the next, by going to the next step. I have a square, and in the square I can draw a diagonal. And when I draw a diagonal, I have two possibilities. I can do it in the left way, like this one, or in the right way, like that one. So from the lower left corner to the upper right corner, or the other way around. And when I use these two pictures to make a piece of art, I could make a piece of art like this, one square with one diagonal. And if I choose another random number, could be the same, could be a different one, but each time when I choose a random number, I get a diagonal, and sometimes it's going to the left and sometimes it's going to the right. Now, a computer can calculate things repeatedly, And I could repeat this process by dividing this square into 4 new squares. So when I take the midpoints of the edges, the red edges of this big square, connect them, I get 4 squares, and I could in each square, new square, do the same thing I did in the big square, and then I have a picture with 4 diagonals, and randomly chosen. When I choose another times, I have a lot of possibilities. The number of possibilities is 2 to the power of 4, because I have 4 squares. And I can repeat this process in Python very easily, because the function that it does is exactly the same. The only thing that differs is the place where the square has to be drawn and the number of squares. Now, if I make a subdivision in the same manner I did, I have 16 squares. And if I leave out the gray lines, I have a piece of art that is built up from 16 squares, and the number of possibilities is 2 to the power of 16. And so I can go on with a new painting, and each time I make this painting with the same number of squares and now have 64, then choosing in each square a random diagonal, I can make a new picture. And when I go on and go on and go on, I have here 4,069 squares, and each square has a random diagonal, and I see this picture. Now, you could ask how many squares, how many possible pictures I can make in this way. Well, that is 2 to the power of 4,096, and Python has the possibility to calculate this and see the number. I'll calculate it. I'm now in Python shell. It's a kind of calculator page in Python. 2 to the power, and Python has a way to write this as 2 times characters, 2 to the power of 4,069, and this number is very big. It is, well, it doesn't fit on the screen. So this is the number of paintings I could make in this way. Now I can make new paintings, but now use not the diagonals, but take quarter of circles, and I choose 2 different tiles. One, the left one, is a square where the midpoints are connected with a piece of a circle, and here in another way. And if I make in the same way as I did before a painting, I have, when I use 1 square, 2 possible paintings, and when I divide it, I have 4 squares, so 16 possible paintings. And when I leave out the subdivision line, I have a painting and another one and another one and another one. And so I could do the same process. It's the same, exactly the same program I used in the previous example with the diagonals. And I can make a lot of nice patterns just by drawing quarter of circles in a random way. And a question you could ask your students is, why are all these lines continuous? Well, these are nice discussion questions you could discuss with your students. Okay, this is not a course in Python, so I'll not go into the code I used for this, but it's just examples what you can Python use for when you want to make coding, let's say, appealing to students. I could do the same thing, but now not drawing diagonals or lines or pieces of a circle, but just color pieces of the square. I here have 7 different squares, and when I use these patterns to make the same kind of painting, I have a big painting with, in this case, a diagonal and colored at one side and the other side is white, or this one, or that one, or that one, or and so on. I have to choice randomly out of 7 different possibilities. And when I make a painting with 4 squares, I could see this, or this, or this. And when I make another subdivision, I have a new painting. And each time I choose randomly a shape, I can make a new picture. And this looks very nice. It looks a bit as the art of the late 1960s called op art, when what was very popular to make black and white pictures. Now, black and white is for some people boring, so you could also add colors. And I have chosen 4 colors, black, if you want to call that a color, blue, yellow, and red, and randomly color one of these tiles I choose each time with a random choice from these colors. And when I make then a picture, I have a big one with the same patterns, same shapes, but each time in probably another color. And when I make subdivisions, I can make a piece of art but looks like a Mondrian, that's a Dutch painter, who uses patterns like this and colors like this. So this could be a nice project for students to make what we call computer-generated art. So the basic is what I showed you the first time, the choice from 2 different squares with diagonals, and exactly the same program, the same algorithm you can use for arcs, for shapes, and for shapes with color. Another example of art, you could use it, call it art, is just drawing circles on the screen and choose the right place where to draw them, and then when you fill the whole screen with just circles, or I have to say discs because I make them white and only the edge is black, so they overlap each other. But now I can make just a small loop and place circles on the screen on the right spot, and when I go on, I can fill the screen, and when I filled it, it looks rather nice, I think. It looks like semicircles, like waves, or what you would want to call them. And now you can play with this. You can, for instance, color them. The code for this is, these are all the lines of code, 2 loops, 1 for the horizontal and 1 for the vertical. And the only thing is trying to find out where the center of the circles have to be and how big the radius is. And that is what, if you do this with a student, is the challenge. And in this case, what I shown you now is that I also use a shade of gray to color them, and then you have some depth in your painting. And you can use the same algorithm, but now use colors, the rainbow colors, and now you have a lot of rainbows on the screen, which form a new piece of art. Back to the 60s, and no, I mean to the 70s and 80s of the former century, then you had screensavers, and a screensaver is nothing else than a line or more lines that go over the screen and take new positions to prevent that the screen was burned in, damaged when a pixel was lit too long in the same color. Now, a screensaver in the early computing age was more like this. You had a lot of lines, and they waved over the screen and followed a pattern. And the thing is, how do you construct this? Well, I go back to one line, and I made this just by, and this is a math for students in the upper classes. I just took two parameter curves. I'll show them, a red one and a blue one, and a point on the red one and a point on the blue one are connected, and I take how do you say it? I don't know. Well, I let the point follow the curve, the red one, and the other point follow the blue curve. And when I connect it with a segment, color it green, I have this line that waves over the screen. And if I take more points close to each other, they are the same, follow the same curve. And now you can see how you can construct such screensavers on, well, let's say in a mathematical way, using parameter curves and, well, that using parameter curves. When I use other curves and more lines and more colors, I can make it more interesting. And now I have a lot of colors and some different curves and more lines, and color each line in its own different color. I have a screensaver, what looks like a piece of art. It's moving and changing shape and changing colors. This is what you can do with Python just by using some mathematics. Now,
thanks a lot, Bert. I think at this point, do you want to show some more examples, or shall we go to some questions from the audience?
Oh, it's up to you. I have a lot of examples, so.
Well, we have 10 more minutes and we have a couple of questions.
Okay.
So I would suggest let's move on to the Q&A part.
Yeah.
And for this, I would like to go back to the slides. And first of all, we received some questions on the software that is being used. Can you remind, or maybe Koen, can you remind the audience of what software
the software
you use for this?
Is TI Inspire CX software, and you have a student version, but you also have a teacher premium software. And you can find it on the TIeducation.ti websites of each country. And for teachers, normally they can get a free software for that. And it's the same software that runs on a handheld, on an iPad, and on a Mac and on a Windows machine. For the iPad, we don't have Python in it. But for the handheld and Mac and Windows, you can, what Bert was showing are documents, and those documents you can exchange between the handhelds and the software. So you can use it in a handheld mode, but you can also use it in a standalone software mode.
All right, thanks for this clarification. And we also received a question from Rifat asking if you could perhaps share these presentations. For sure, the presentations will be made on the STEM Alliance website, and we will share the link with everyone who attended today, but also the codes shown in the examples.
No problem at all.
Perfect. So also this will be made available on the STEM Alliance website. And we had a bit more of a technical question from one member in the audience, which is the IDE being used? And I believe with the IDE, it's the Integrated Development Environment that was mentioned. Can you elaborate on that, perhaps?
Not really. So it's MicroPython that is integrated by our software engineers in the TI Inspire CX software. And how that exactly is done, I don't know. And I also don't think they're going to share it with us.
All right. Now, moving on beyond the codes, I wanted to share one more question on a general approach when we talk about computational thinking, and also an elaboration of these this webinar series. In the discussions I had with you and the colleagues from Texas Instruments, we noticed that when a lot of people talk about computational thinking, it's more about computational. And maybe I would like to pass this question on to the audience as well. What part of computational thinking do you believe is more important? Is it the computational or is it the thinking? From our side, we believe it's the thinking, and maybe Bert or Koen, this part of thinking, maybe can you see how this is relevant in a broader sense of joining mathematics, but also other subjects in school?
Bert, you first, then me, or?
Well, you first. I'm thinking.
Think a bit. So what we try to do is making a lot of representations of concepts available in the classroom, and programming is one of them. And for programming, you need to have a lot of thinking, where, let's say, 10, 20 years ago, programming was already more integrated in mathematics, but that moved away completely. So the thinking, the algorithmic reasoning, logical reasoning, it's all connected to mathematical thinking and mathematical skills, and reasoning skills, critical skills. And it's also a way of doing mathematics to motivate students more to tackle problems and to get engaged to solve a problem and to get an understanding of it. With computers, also next week it's about also controlling microcontrollers, having more visualization of the code, visualization and solving a problem, engineering, this kind of stuff, bringing that all together. And the computational kind of the side of it is more that, hey, how can you now use technology in a valuable way to motivate students to do mathematics and science and engineering? And as you know, Texas Instruments is an engineering company, and we have also a huge need on engineers to develop our future products for optimization and sustainability and other stuff. So how to engage students to do it in mathematics, but also for next week, we try to connect mathematics with science and with computer science, etc., etc. So let's say that's how I look at it.
Yes,
Okay.
And for me, it is when you have a problem, it could be a mathematical problem. It could also be what I showed, a graphical problem. You always have to think, how can you divide it in sub-problems, make it small steps, and then in which order do you have to follow these steps to come to the result. And I think this is the basic of computational thinking.
All right, thanks a lot for...
That's my meaning.
Yeah, but I think this is interesting because it goes beyond the mere mathematics, but it actually looks at something larger when it comes to the 21st century key skills, for instance, and different competencies among students. So one other question I received was, for the examples that you shared, what age group would you think this is appropriate for?
Well, this depends on the example. The very first example could be done in a very low grade and young student group, because it's only using a random function and nothing else. But when you come to, let's say, this example of the screensaver, you cannot do this with young students, because you have to be able to do some mathematics, and that is in our curriculum in Holland only for the students that are aged 16 or something like that. So it's depending on what you want to do with your students. It depends on the example.
And it depends on the curriculum. So the mathematical examples I have shown you are in some countries, depending on, as I said, on the curriculum, but it's mainly for middle school to upper secondary. In some countries you have the statistical stuff, you have it in middle school. In some countries you have it in the last years of secondary. But let's say we tried also to show examples to show the power of that combination, and it can also be done with other topics, but then much easier ones in primary school. But these examples are more for secondary level.
All right, great. Thanks for this. Then one question I will answer, well, partially with a cliffhanger. We received a question if this could be integrated in English class or in other classes beyond maths. And I think for this, perhaps tune in next week on Thursday at the same time when we will look at the second series, or the second webinar of the series, where we will extend the scope a bit. Now, at this point, I think it's time to wrap up, and I would like to mention once more that it is very crucial that you validate your attendance in this webinar via this digital signature list. Now, we have several links. Please try out which one works. Perhaps also try it in different browsers. Sometimes that could be an issue as well. But if you would like to receive a certificate of attendance, this is the only way to request one. And for those of you who are watching the recording of this webinar, please note that only participants who attended live will be able to receive a certificate. We will also share with you a feedback survey, and this should also be shared with you right now in the Q&A chat window, so you should be able to share your feedback with us right there already at this point. We would really appreciate if you took about 3 minutes of your time to share your thoughts and feedback on today's webinar, so we can improve in the future. And of course, we will also share this in the follow-up. Now, I would also like to share, if you're interested in the activities of the STEM Alliance, that we have recently launched the STEM Alliance LinkedIn page, and also here you can follow the link. Finally, as I mentioned, and as you know, this webinar is part of a mini-series of webinars co-organized by the STEM Alliance, Scientix, Texas Instruments, and T-Cube Europe. And if you've enjoyed today's webinar on computational thinking, why not join next week again at the same time when we will cover the topic of physical computing with Python in the classroom again with Koen and myself, and we will be joined by Cathy Baars, a physics teacher from the Netherlands. Now, the recording of this webinar together with the slides and also the coding examples will be available on the STEM Alliance website in the following days. We will also send you a follow-up email with all the details you need. And at this point, I remain to thank you so much once again, Koen and Bert, for your presentations. And thank you to the audience for the really interesting question. That's all from my side. Take care and stay safe and have a nice evening. Bye-bye.